Hey everyone, just back with our next lecture video. This is lesson 3, chapter 5 lecture on earthquakes, and we will get to this. I've been looking back at the views on some of these videos. I see some of you are getting started a little bit later than I would like to see. The next couple of these lecture videos I'm going to try to make a little bit shorter, just hit the highlights. I'm not going to discuss as much um, about these. I want to focus more on later in the semester getting to the environmental issues that we face. And these, while these are important, they're natural disasters, and you do need to understand how these function. I'm not as interested in all the minute details of these lessons, so I just want you to understand basically what I discuss and the primary topics that are covered in your textbook. So, earthquakes and related hazards. So, most of us have heard about earthquakes in the media. Probably very few of you have experienced any, especially if you have lived locally most of your life. We do have some earthquakes in this area, and I'm going to touch on that in just a little while. But for the most part, we don't have to experience a lot of earthquakes locally in the Kentucky area. So just a couple of examples here before we really get started into the nuts and bolts of this is most of you thinking back, this seems like it was yesterday to me, but this was probably when a lot of you were still very, very young children. The Indian Ocean tsunami that occurred, it occurred as a result of an earthquake that happened on the ocean floor. It displaced a lot of water, and it caused this tsunami, or tidal wave is what we used to call these things, if you've heard that term, to come in and completely devastate some islands in the Indian Ocean. And you can see here a before and after pic. This was before the tsunami hit, and after it pretty much just wiped everything man-made just completely out. So this is the destructive power, and a tsunami is going to be a related hazard to the earthquake. The earthquake itself will cause damage from the waves that it sends and the shaking that occurs. But if it occurs, say, on the ocean floor like this one did in a subduction zone, then that shaking might not be really close to land, but it could result in a tsunami that affects land hundreds or even thousands of miles away. So how does an earthquake occur? So you remember from our last lesson, we have our plate tectonics, and we have those crustal plates that move around on the surface of this planet. So as they move, they encounter each other, they come together, and you remember those zones that we talked about, the subduction zones, the transform fault lines where they're rubbing past each other, not crashing into each other, are the divergent plates that are going away from each other. Those boundaries that we discussed is typically where earthquakes happen. And depending on the type of fault or the border between those plates, depends on what type of earthquakes might be experienced in those areas. And this is actually a kind of a good example. It's not moving like a video or anything, but it's kind of showing what happens. So when these plates are coming together and moving together, whether it be past one another or colliding into each other, there's a lot of force being exerted on each plate. So the rock layers are scraping against each other. So they use iron and wood here as examples. In this case of iron, it's a metal, and if it's thin enough, it can be, they call it ductile. That means you can bend it. So think about these rocks kind of deforming or bending a little bit. Even though rocks we think of as brittle, sometimes they have properties, especially if it's a fault that they have heat associated from below, that they can be more ductile. So they might bend and deform a little bit as they move past or into one another. And if that's the case, that pressure will build up over time. Think about it, it's kind of like winding up. The more it goes without a release of that pressure, the stronger that force is, until eventually it pops. It breaks. And when that break happens, that's when you have an earthquake. So a good analogy to that is if you look at the little man, the little image on the right, he has the wood stick, and it's brittle. So you bend that wood to the point, it'll bend a little bit, but eventually it's just going to break. And when it snaps, when that break happens, that's the earthquake happening. And you can think about the sound waves that come. You know, you hear the snap of the wood. Think about those sound waves as the waves in the earth that create earthquakes. As they move away from that epicenter, that focus, they travel through the ground, through the rock, dirt, whatever the media is, and as they move away, they move it. And those waves are moving that strata as they move out. And that's what causes the ground shaking in an earthquake. So if you can put that in your mind, think about those as those sound waves that move away. Of course, if you break something, the stick, it's going to be the loudest right next to it. You might hear it in the next room, but it's not as loud. That's how those waves act going through the ground. So this kind of is an example of what I just talked about. You can see the different diagrams here. These are in their textbook. These are at rest. These are before an earthquake happens, but they're starting to deform just a little bit. If you live in an area that has a lot of tectonic activity, you might go out in your yard one day and see a fence that might be leaning. Or your driveway looks a little bit off. Not much, but you might notice a little difference. If you have like a retaining wall, it might have a crack in it one day. That means things are moving a little bit. And then the bottom left picture, diagram is after these things, that focus, they call it the epicenter here. I'm going to go into these terms in just a second. Where that break happens, it's going to snap. And when it snaps, those waves emanate out from that point. And then it returns to it's released that pressure. Now it goes back to being more static as far as what we can see and what we can feel. Now, that might return, depending on what type of fault it is, it might return to a situation like this. You see this road was actually moved several feet. That happens. Not too much around here, but out west where you have the transform faults, or what we used to call the strike slip faults is what we used to call them in geology. That is very common for things to get displaced by several feet, and then you just have to fix them. They're never going to go back, of course. Now, if it's a different type of fault, like a subduction zone, you're going to have a lot of shaking, but it might not linearly displace like that on the surface. And you can see here just an example in a field where the vegetative rows are kind of off a little bit. So this is just a very simple line diagram. Basically just showing the waves. A larger, more powerful earthquake happens when that strain has been building up over time. Like I said, that strain starts out as small, and if it's not released over time, it's going to get more and more and more. And when it does pop, when it does break, it's going to be a very strong earthquake. So that should tell you that in areas that have earthquakes a lot, like I was speaking in the last video about Lima, Peru, they have them all the time. So it's not really common for them to have a really, really, really big earthquake, like up in the 8s or 9s. They do have some pretty good earthquakes, especially what we would consider here as pretty good earthquakes. But for down there, since they have them a lot, those strains are being relieved through those smaller earthquakes. So you don't have a huge earthquake. If you have a fault that we'll say is overdue, let's say they've traditionally had really big earthquakes and there hasn't been one for 100 or 200 years, then those areas are more likely to experience a large one sometime in the future. Again, we're talking about geologic time here. So that might be way after any of our lifetimes. It might be tomorrow. We just really don't know at times. So earthquake waves, I'm going to get into this in just a little bit. I'm not going to get real detailed about it, but waves, like I said, you can liken them to sound waves that travel out when a noise is made through the air. It's the same principle, except they're moving through the ground, much stronger. There's 2 or 3 different kinds of waves. Surface waves are the waves that really get us as far as damage and what we feel the most. There are P waves, S waves. I'm going to talk about those in the next slides. A seismograph is an instrument that measures seismic waves, so that's what gives us the strength of the earthquake after it's done. Actually, when they do measure these earthquakes, they triangulate between 3 of these locations to get the epicenter, where that point is on the surface where the earthquake happened, and the strength of the earthquake. So they're actually using 3 different stations to get that. The focus, or the hypocenter, is the point within the earth where the earthquake occurred. So think about that in 3D. Not only the epicenter, the bottom one, that's on the top of the surface. So let's say the epicenter was in Los Angeles, California. That's the epicenter, that's on the surface. The hypocenter might be 3 miles below Los Angeles in the ground, down in that plate. That's a difference in the focus and the epicenter. I mentioned the seismograph. It's just an instrument. I'm not going to get into mechanical details of this. Basically, it's just a little mechanism that has a pin attached to it, and when it shakes, that pin shakes and moves on the paper with regards to that shaking. It's a very simple little machine, but it will measure these waves. And again, I mentioned the P waves are not so destructive. They move very quickly through the earth, and they arrive first within just a few minutes difference in the P waves, and then with surface waves. The S waves are the secondary waves that arrive. They're a little bit more destructive. They tend to move the ground in an up and down manner, not side to side, but they arrive second. And then the surface waves arrive last. This is what we measure the amplitude or the strength of the earthquake on. And this is what really shakes and moves the surface of the earth. Think about it. You think about an ocean wave. If you stood to the side of an ocean and you watched the waves crashing down on the beach, that's what these waves kind of look like, except they're moving through earth. So they're heaving up and going down as they travel. So that's why they're so destructive. And again, here's the summary of what I just told you about the body waves. The primary waves and the secondary waves are in the ground, and the surface waves are on the top of the ground. They arrive last, and they are the most destructive, as I mentioned. And here's a little diagram also of what I just discussed. The primary waves get there first. You see the kind of side-to-side motion, the cracking of the earth. The S waves kind of heave up and down a little bit. And then the surface waves are actually, like I said, if you look, it looks like a wave in the ocean. They move kind of rolling through the surface. So here is just some diagrams of how they measure that epicenter, where the epicenter would be. You see the different stations here plotted on the map, and how they measure, they triangulate these areas and find out where that epicenter is. So, and they can do that worldwide. The stronger earthquakes produce waves, even if they have it on the other side of the planet. We can detect those here in the United States. We have a few different scales of measuring these. There's an intensity scale. I'm not going to go into that a lot. The magnitude scale, the Richter scale, is what we're most familiar with. That's what we always talk about. When we say an earthquake is like a 5.0, that's a Richter magnitude scale. This is a Mercalli scale. Like I said, I'm not going to focus on the Mercalli very much. The Richter magnitude scale, one thing to keep in mind here is when you hear these numbers, like you hear a 4.0, a 4.5, a 5.0, those are measures of intensity, how strong this earthquake is, the ground shaking, the ground motion. And for each number, this is an exponential scale. You see this line. It's not in a straight line. So, in other words, a magnitude 4 earthquake is not just twice as strong as a magnitude 2 earthquake. It's going up exponentially as we increase. The way these numbers work, it's actually a magnitude of 10 for each whole number you move. So, a magnitude 4 earthquake, a magnitude 5 earthquake is going to be 10 times stronger than a magnitude 4. A magnitude 6 earthquake is going to be 100 times stronger than a magnitude 4. So you can see when you get up in these numbers higher, the tremendous damage that could be done up in this 7, 8, 9 area, because we're going up exponentially. When we have magnitude 3 and 4s around here, that's not terribly uncommon. Sometimes you probably won't even feel a magnitude 3 depending on what you're doing and where you are. But you're talking about a much, much larger earthquake when you get up 7, 8, or 9. Again, we've already talked about plate tectonics. Transform or strike slip boundaries, that's San Andreas, that's in California. That's what we're used to hearing about all the time here in the United States. So they have quite a few earthquakes over time. Convergent boundaries, the subduction zones, remember that's where two plates come together and one kind of goes under the other. Those produce earthquakes as well. They tend to produce not as many, but bigger earthquakes. That's just a trend. That's not saying that they cannot produce smaller earthquakes. They absolutely do. But over geologic time, you have more of a likelihood to have a much larger earthquake around a convergent boundary than a transform. But they can happen at either one. So don't take that as me saying they don't happen at both. It's just the frequency and the types, or there's a pattern in those. Again, here's a subduction plate going under the surface. And you can see where the epicenters are of these earthquakes. Some of them are out here right on where the subduction is starting on the surface. But you see this plate's actually continuing down and continues down until it starts melting deeper. So you could have epicenters all the way out here. They just occur deeper in the earth. So if you have an earthquake here, the focus is going to be, or the hypocenter is going to be shallower than the hypocenter would be in here. So that's something to keep in mind. You probably will see that diagram again. And here's a plot. This is California showing magnitude epicenters. I think that's epicenters. 7, the big circles, the red circles are magnitude 7s, and the 6s are smaller, are the greens. So we're talking about the plate boundaries. And I mentioned that we do have some earthquakes here at times. And if you did your assignments in your previous lesson, you know that Kentucky is nowhere near a plate boundary. So what's going on here? So from everything that I've studied, we have these very deep fault lines under the center of the North American plate. It's theorized that at one time in geologic history, millions and millions and millions of years ago, probably billions of years ago, there was actually a boundary here, but it is no longer active. And the crust is formed over this boundary. So it's no longer an active plate boundary, but there are still faults under the ground. So still weaknesses in the rock. So sometimes pressure is released from these faults, and we have earthquakes here along the Mississippi River. If you look at this map here, this is the Mississippi River, the black line around through here. You see the city of Memphis. Nashville would be about right here. We would be about right here at the bottom of the K, maybe bottom of the Y, right in this area is where we are. So as you can see, we do have quite a few earthquakes here in this area. Most of them are weak enough that we don't feel those, but nonetheless they happen. In history, there have been a few really, really large earthquakes that have happened in this area. Specifically in 1811 and 1812. Now, if you think about what was going on in 1811 and 1812, Kentucky was being settled, but there weren't a lot of settlers here. It was early in our history of the United States, so there were people around that documented those earthquakes. Not a lot, but there were some. So the damage was kind of not major because there wasn't a lot of human structure out here to damage. But the damage to nature was evident. You see several oxbow lakes that were created in the Mississippi River because the river changed course in places. It was that strong. It was noted in one city in New Madrid, Missouri, that the river actually flowed backwards upstream for a period of time because of the shaking and the displacement in the ground. So this was a very, very large earthquake. Do we have the potential for that to happen again? Yes, there's always potential. In our lifetime, potential, yeah, anything. Never say never. But unlikely, yes, it's very unlikely that we have another major earthquake like that. Of course, I should knock on wood. I don't want it to happen anytime soon. But we're just not a really active fault, but it does happen here. And these are some other examples of that. Now, another thing I want to mention here is we're going to talk about the effects on us, humans, and our structure a little bit later in this slideshow. So one of the really dangerous things about faults like we have, and here is one down and around the South Carolina area, you saw one earlier up in the Northeast, is that we are not used to earthquakes around here. And as I said, the last major one was in 1811, 1812, basically before we started building any of our current infrastructure here. So there are no building codes for earthquakes. So we construct our infrastructure, our roads, our homes, our businesses, any buildings, we don't take that into consideration. So in California they do. They have codes out there to make buildings withstand earthquakes a lot better than we do here. So if we do have a moderately big earthquake here, it's going to cause a lot of damage to our infrastructure because we simply are not prepared for that. And here are some examples of how the ground waves will make buildings start to sway and shake, where they can actually fall down, come off their foundation, or at least in this case make them unstable to enough you're going to have to tear it down and start over. There's no way you could utilize these buildings any longer. And that's what I'm talking about, how we build our buildings here. We don't build them to earthquake codes that they might have in other places. Again, another example of this, how the buildings start to sway. And once that swing starts, as long as that shaking continues, it kind of feeds on itself. It kind of produces its own energy, and it'll continue to sway and sway and sway until it becomes very unstable or comes down completely, like this fairly large building came down completely on itself. And again, we're getting into the damages that occur to our infrastructure. You see the buildings that have collapsed. You see a lot of times people do survive these, surprisingly. But because they're, if you happen to be, say, in a bathroom or a more stable room, you might have a void in that collapse, and that's why there's a lot of efforts after a large earthquake to go in and try to find people. However, you can imagine when you have all this mess that's just falling down, how unstable that is. So it's very dangerous for even the rescuers to go in there and try to find anybody. So it compounds, the problem compounds with itself over time. Now going back to the waves, the focal depth, the wave attenuation, and the ground amplification. I'm not going to get in a lot of detail on this, but basically you have a certain wave length that travels under the ground, and depending on a lot of factors, including what kind of soil, what kind of bedrock you have, the moisture content, that affects how this wave acts and how it shakes things on the surface. So there's a lot of factors that go into this on how much damage is done and how hard it actually shakes on the surface. As you can see here, these are pretty good diagrams. So here you have bedrock. So let's say the earthquake starts down here in bedrock. The waves of that earthquake in very dense bedrock travel pretty tightly, fast and tight. So they don't deviate or have large wavelengths as they're moving. So if it stayed like that, it wouldn't be quite as destructive. But as it gets out here into the loose sediment, this shaking starts to amplify because this is less dense material. It can come apart a lot easier, and depending on soil moisture and what type of soil it is or what kind of bedrock it is, you can really have amplification of these waves. And you see here, down here's an example. So let's say you have limestone bedrock. So that's not as dense as granite or basalt, but it's still going to contain those waves. It's going to amplify, but not a lot. And you can see that up here. As you get into something like loose sand, you see it starts to shake a lot more, and this sand's going to be very unstable because the grains are actually moving away from each other. They're actually jarring around under the ground, and they're no longer in contact with each other. It gives them stability. And then wet clay, you've got moisture, you've got smaller particles. that's almost going to liquefy, and it's going to become a fluid that actually moves. Like you'll see whole hillsides just come completely down if you have stuff like that. So in addition to that, this is kind of a different view of that, but this is more of a 3D kind of if the earthquake's down deep. So here's your bedrock crust, probably granite, maybe basalt if it's on the ocean floor. And you can see how these waves come up and move through stuff. It's going to move in the same manner all the way through the same kind of rock. But as it hits other types of rock, in this case, when you see the little lines that look like bricks, that's always a symbol for limestone. So let's say we have limestone here. So it's going to move through limestone similarly. It might amplify just a little bit, as you're seeing here. That's wave amplification, so it's going to be a little bit stronger, but it's probably not going to keep moving in a similar manner. But once you get up into less consolidated material, like your soil up here, you're going to have what's called reflection, which means it's going to start bouncing off the rock and kind of going in circles, random movement. So instead of a linear movement like a wave, you have it just shaking in general, like chaotic all around. And then you have refraction. And refraction means it kind of just subtly changes direction. It might hit the limestone and kind of go a different way. And what that does, though, is that creates different stresses when these waves meet closer to the surface. So there's a lot going on there. It's kind of hard to explain, but basically, the more consolidated, hard rock that you have, the more stable it's going to be. Now, the secondary earthquake hazards, we've already mentioned a couple of these. The liquefaction, is when solid material like a clay, soil that has a lot of moisture in it actually becomes viscous. It actually can move like a liquid, and you have that moving, and just buildings come straight down in that. You got disturbance to the land surface. Fires are a common thing just because of human infrastructure. Our gas lines break. So you have fires from that. Buildings, the electrical grid gets disturbed. That's why we have fires. And of course, after a major earthquake, it's impossible to fight fires. So they kind of grow a lot more than they should after an earthquake. And then we've already discussed the tsunami earlier. And here are photos of each one of those: a tsunami, the ground displacement, liquefaction, and the fire that we just mentioned. And here is a diagram of tsunami. I have a video of this. I suggest you watch that video in the lesson plan. Basically what happens is you have a very large earthquake that happens on the ocean floor. The ocean floor might drop or rise by a considerable amount, maybe up to 100 feet or so. And all that water that was there gets displaced. And when it gets displaced, it moves up or down very rapidly, creating a very large wave. When you're out in the open sea, you don't see this wave as much because there's waves everywhere. It's not as obvious, but waves keep their wave heights, and when they get to shallow water closer to land, all of a sudden that wave is really growing and really intimidating. And we've had a few instances of this in the last 20 years. You saw one there in Indonesia at the beginning of the presentation. We had one in Japan a few years ago. Several of you might have seen that on the news. There are plenty of videos on both of these online. I shared one with you in a lesson plan, like I said. And these are just absolutely destructive when they hit. When we have early warnings for these, we don't really have an early warning as far as we know it's going to hit. It's just, okay, we've detected an earthquake under the ocean floor, or there's been an event on an island somewhere, and this might happen in this area. So be on alert. And the only way to get away from one of these is going to higher ground. As far as predicting earthquakes, it's very difficult for us to actually accurately do this. There are some tendencies in nature that we see. If you observe a lot of land movement beforehand, like slightly cracked soil, the elevation of the land's changing a little bit. You see a little hump or a little hill here and there that you might not have seen before. Water levels change in rivers and lakes. If you see gases bubbling up from lake bottoms, that is a sign that something might be coming. And again, these are things that we don't experience much here in Kentucky, but in California, people would tell you, yes, they see this stuff happening out there. Long term, the only thing we can really do is say, hey, this is a precarious situation on this fault. It has a high strain capability, and there has not been an earthquake here in a very, very long time. So it's possible that there might be one here in the coming years. A seismic gap, you'll see this term in your textbook. So you have all these earthquakes, pretty large earthquakes happening along this fault line, but right here, there's kind of a gap. There hasn't been one in this area. So what geologists speculate is that this area, because this fault does continue around this area, is probably due an earthquake before these other areas would have one. That's what we refer to as a seismic gap. And here's your seismic hazard map in the United States. Of course, the West Coast, California, you have your strike slip fault or transform fault all along the California coast. Up here, it kind of turns into a subduction fault. So you have a little bit different type of fault up here, and you have more volcanic activity up here as well. And then you have this interior area that we discussed earlier that we don't have really a plate boundary, but we have some ancient faults that have potential. Reducing earthquake risk, I mean, there's nothing we can reduce about earthquakes happening, first of all. I want to get that point across to you. That's going to happen. It's nature. There's nothing we can do about that. But what we can do as human beings is, first of all, I mentioned this before, in this area, we can engineer better. In California, where earthquakes are common, they have certain codes that they have to build by to make their structures less susceptible to collapsing and killing people. That engineering, I'm not going to get into that a whole lot, but they can reduce the force of the shaking. So that's one thing we can do. Early warning systems is something else. We don't have any early warning systems that we can say, hey, we're going to have one in 10 days. We don't have anything like that. But we can say, hey, we've seen this activity. We've seen an increase in activity in this area. Everybody just be prepared in case something happens. Another thing we can do is we do have some sensors out there that can detect these remember the P waves, the primary waves, they arrive first. They can detect those before the earthquake waves actually arrive. So in something that's really quick, we can actually shut down gas and power lines when we detect those so that we don't have the fires and stuff like that after they arrive. And then planning and education, just simple education to citizens and proper zoning laws to maybe stay away from certain areas that are really, really susceptible to damage. So again, the early warning systems, if we can detect these P waves from these sensors, we might be able to cut off gas and electric up here before the actual earthquake waves hit. The engineering, you see these in your textbook, and that's the conclusion of this lesson. So again, if you need any help with anything, feel free to let me know. We're just getting into the semester. These double chapter lessons are as hard on me as they are on you. So I don't like them anymore. This should be the last one we do this semester. From this point on, we'll only have one chapter per lesson. So thank you guys for hanging out. And if you need anything, just let me know. Thank you.